Hello! In this video, we're going to prove the following theorem. The golden ratio is irrational. Now, by definition, the golden ratio is equal to 1 plus the square root of 5 over 2. So one way to prove that the golden ratio is irrational is by using the fact that the square root of 5 is irrational. And so the way it goes is, if you assume for a contradiction the golden ratio is rational, while solving for square root of 5, we see that the square root of 5 is equal to 2 times the golden ratio minus 1. So, 2 is rational, the golden ratio is rational, and 1 is rational. We know that a product of rational numbers is rational, and a difference of two rational numbers is rational. So it follows that the square root of 5 is rational, which contradicts the fact that square root of 5 is irrational. So we've reached a contradiction. Our assumption that the golden ratio is rational led us to a contradiction. So we must instead have that the golden ratio is irrational. So that completes the proof. But in this video, we are going to look at a proof that the golden ratio is irrational, which doesn't use the fact that the square root of 5 is irrational. And so our alternative proof is motivated by the following geometric construction. Let's consider a rectangle where the ratio of the longer side length to the shorter side length is equal to the golden ratio. Well, then it turns out, if we split up our rectangle so that here we have formed a square, well then we've also formed another rectangle. And it turns out the ratio of the longer side length to the shorter side length in this rectangle will still be equal to the golden ratio. Well then, continuing in the same way, if we take this rectangle and split it up so that here we have a square, well then we formed a smaller rectangle, and the ratio of the longer side length to the shorter side length is still equal to the golden ratio. So then continuing, we split up this rectangle so that right here we formed a square, well then we formed another rectangle. And it turns out the ratio of the longer side length to the shorter side length still equal to the golden ratio. So then we split this rectangle up, say like this, so that right here we have a square, and then above we have another smaller rectangle. And it is still true that the ratio of the longer side length to the shorter side length is the golden ratio. So then doing that again, we split up our rectangle so that right here we have a square, right here we have a smaller rectangle. And it is still true that the ratio of the longer side length to the shorter side length is still equal to the golden ratio. Right? And we can continue doing this forever and ever, so that we construct a new, smaller rectangle where the ratio of the longer side length to the shorter side length is the golden ratio. So how does this motivate a proof that the golden ratio is irrational? Well, if we assume for a contradiction the golden ratio is rational, then we can express the golden ratio as a ratio of positive integers, say a and b. Since the golden ratio is greater than 1, we must have that a is greater than b. So then let's take our rectangle right here, label the longer side length as a and the shorter side length as b. Well then, the ratio of the longer side length to the shorter side length is equal to the golden ratio. So then, by our construction, if we consider this rectangle, we know that the ratio of the longer side length to the shorter side length is equal to the golden ratio, right? And this side length, by the way, is b. This side length is a minus b. So what that's telling us is that we can reduce this fraction to b over a minus b. But then continuing, we have this smaller rectangle. It is still true that the ratio of the longest side length to the short side length is equal to the golden ratio, which means we could reduce this fraction even further. But then going to the smaller rectangle, which we have right here, ratio of the longer side length to the shorter side length still equal to the golden ratio. So we can simplify our fraction even further. But then looking at this rectangle, ratio of the longer side length to the shorter side length still equal to the golden ratio, so we can simplify our fraction even further. So then going to this rectangle, ratio of the longer side length to the shorter side length still equal to the golden ratio, so we can simplify our fraction even further. And this construction continues forever and ever, so that you can continue reducing this fraction forever and ever and ever. But if we have a positive rational number, we should be able to express it as a ratio of positive integers, but then we should be able to simplify that fraction so that eventually we reach a simplest form, so that the greatest common divisor of the numerator and the denominator is equal to 1. So we should be able to simplify this fraction so that eventually we reach a simplest form. But this geometric construction shows that we could simplify this fraction forever and ever and ever. So there's a contradiction in there somewhere, right? And so this is our motivation for our proof that the golden ratio is irrational. So now, let's get into the proof. Right, we're first going to write down some results that we're going to be using in our proof. So the first result we're going to be using is, for every positive rational number q, there is a unique pair of positive integers a and b, such that q is equal to a over b, and the greatest common divisor of a and b is equal to 1. Right? This first result is telling us that every positive rational number has a unique simplest form, essentially. Our second result describes what happens when the greatest common divisor of two integers is equal to 1. So given that a and b are integers that are not whole 0, then the greatest common divisor of a and b is equal to 1, if and only if there exists a pair of integers s and t, such that as plus bt is equal to 1. Okay, so now let's get into proving that the golden ratio is irrational. So to start out the proof, let's assume for a contradiction that the golden ratio is rational. Well, we know that the golden ratio is positive, so then that means the golden ratio is a positive rational number. So then, according to our first result, there is a unique pair of positive integers a and b, such that the golden ratio is equal to a over b, and the greatest common divisor of a and b is equal to 1. Now let's note, the golden ratio is greater than 1, so we must have a is greater than b. Now, a over b is the simplest form of this fraction, right? That's essentially what this is saying. But our geometric construction suggested that we should be able to simplify this fraction even further. It suggested, more specifically, that we should be able to simplify this fraction to b over a minus b. So, to see how this happens, well, this comes from what the golden ratio really is, right? By definition, golden ratio is this quantity, but it's also, therefore, a solution to the quadratic equation x squared minus x minus 1 equals 0. Right? So, golden ratio squared minus golden ratio minus 1 is equal to 0. So then what we're going to do is, we're going to take the first two terms and factor out the golden ratio. So then this is just the golden ratio times the golden ratio minus 1 minus 1. So this is equal to 0. Well then, adding 1 to the other side and dividing by golden ratio minus 1, we get that the golden ratio is equal to 1 over the golden ratio minus 1. But then let's substitute this golden ratio for a over b. So this is just 1 over a over b minus 1. But then if we multiply both the numerator and denominator by b, this gives us b over a minus b. So the golden ratio is equal to b over a minus b. Now, the claim is that the greatest common divisor of b and a minus b is equal to 1. And to show that, we're going to be using this result. Now, since we know that the greatest common divisor of a and b is equal to 1, that means there exists a pair of integers s and t such that as plus bt is equal to 1. To show that the greatest common divisor of b and a minus b is equal to 1, we want to find a pair of integers, say x and y, such that bx plus a minus b times y is equal to 1. That will prove that the greatest common divisor of b and a minus b is equal to 1 by this result. So let's see how we could come up with x and y. So we need x and y such that bx plus a minus b times y is equal to 1. So we're trying to find integers x and y such that this is true. Well, expanding this out, this means we would have this. And actually, we're going to group together the terms with b in it. So that means we would have this. Okay, now we know that as plus bt is equal to 1. So if we choose x and y so that s is equal to y and t is equal to x minus y, then that should give us what we want. So we need s equal to y, or I should say y equal to s. And therefore, x minus y equals t. So x minus y equals t. So plugging y in for s, we have x minus s equals t, so that x is equal to s plus t. So, we're looking for integers x and y such that bx plus a minus b times y is equal to 1. Well, if we take x to be s plus t, and we take y to be s, then this should work. And so let's just plug that into our proof now. So I'm writing our choices for x and y here, right? But if we expand this out, this should be equal to 1. So expanding this out, we get this. The bs's cancel out, so we're left with as plus bt, which we know is equal to 1. So this shows that we have found a pair of integers, such that if we do b times the first integer plus a minus b times the second integer, we get 1. So that means according to this result, it follows that the greatest common divisor of b and a minus b is equal to 1. Now, what's the reason for why we showed this? Well, we know that a and b are the unique pair of positive integers, such that the golden ratio is equal to a over b, and the greatest common divisor of a and b is equal to 1. Well, now we have just shown that b and a minus b is another pair of positive integers which satisfies the same conditions. Because, well, first of all, we know that b and a minus b are positive integers, right? A minus b is a positive integer because a and b is the difference of two integers and a is greater than b. So yeah, b and a minus b are a pair of positive integers. And we know that they satisfy both these conditions because the golden ratio is equal to b over a minus b. Also, it satisfies this condition because the greatest common divisor of b and a minus b is equal to 1. So yeah, b and a minus b is another pair of positive integers satisfying these same conditions as a and b. But since a and b are the unique pair of positive integers that satisfy these conditions, that means the pair of positive integers a and b must be equal to the pair of positive integers b and a minus b. So we get that a is equal to b and b is equal to a minus b. So we see that a is equal to b and a is greater than b, which is contradiction. Our assumption that the golden ratio is rational led us to a contradiction, so we must instead have that the golden ratio is irrational. And so this completes the proof. And so yeah, that's pretty much it for this video.